Okay, hopefully everyone can hear me okay. As you can tell, I'm going to be speaking in English, so apologies for that. I have tried to learn German, but I can't even do the numbers yet, so it's going to take me a good few years. I've been to Darmstadt for at least 3 years, and various other places in Germany. I'm still terrible. I can barely remember Danke. So anyway, I'm going to keep trying. Also, I want to say this is my last presentation in Europe until Brexit happens, so I want you to all feel sorry for me. Yeah? So make sure you give me good marks at the end, because I might not be able to come back. Also, if you can't read that, we are talking about delayed durability today in SQL Server. If it's not what you want to watch and you made a mistake, feel free to go. If you think the session's a bit boring, again, feel free to go into another session. I have to warn you, though, if you are the last person in the room, you can't leave. So you're stuck with me. Right, so a quick question. How many DBAs do we have in the room? Wow. That's the most yet. How many developers? Okay, don't fight, you two. How many BI people? Only a few. And is there any managers in the room? There's a few managers. There's probably some that don't want to admit to it. I'd probably say this session is relevant to all of those. From a management perspective, you at least need to understand this technology. If you're a bit of a technical manager, you want to understand what these technologies are that your DBAs and devs and BI people are using, because you want to know the risks to your business. So hopefully it will kind of float your boat a little bit. Quick overview. Actually, we don't want to talk about this. My contact details are later as well, so don't worry too much about this slide now. Quick overview of what we're going to be talking about. So the first part, I'm hoping for some of you at least, will be a bit of a regurgitation of what you already know. We're going to be really looking at what transactions are and how we define them and what they actually do. I also want to demonstrate how SQL Server doesn't adhere to the acidic properties already, or at least some of the acidic properties, because what SQL Server and Microsoft decided to do is, because some of the properties were already broken, by default you can overcome these broken acidic properties by programming correctly, basically. But because some of them are already broken, Microsoft didn't see a problem with breaking the last one in the durability. So I'll be demonstrating that to you first. Then we'll be moving on to something that, as quite an experienced DBA, I didn't really understand the log architecture and how it's really working. But you'll see. I'll explain what I didn't really understand before I really start to research this area. Also, because delayed durability works with in-memory OLTP and just the default on-disk durability, I'll have to explain how in-memory works as well. So if you come to this session to learn delayed durability and come to this session maybe to learn a bit more, you'll learn two technologies there, because I've got, and I'll show you in a second, I've got all the demo which you can take away and you'll be able to just replay the whole thing yourself. It's heavily commented. So really what I'm doing with the demo with you guys is just talking through it, and you'll be able to understand what's going on when you run through the thing. And then, of course, we'll be moving into what the presentation is really about, the delayed durability side of things. What the hell is delayed durability? So I'll be explaining that. And then finally, I'll be talking about some of the limitations and some of the things you maybe want to think about with delayed durability. And finally, for me, I'll probably be nervous wreck by the end of the session, so I'll be having a few gin and tonic somewhere. So how many people here are using SQL Server 2012 or below? Okay, that's quite a lot of people. Of those people, how many of you don't run SQL Server 2014 or above? There's not so many. And of those people, how many of you do not think your company will ever upgrade? Not one person, because that's good, because obviously if you're never going to upgrade, I'm not sure this session's really for you, because delayed durability will only work from SQL Server 2014 and above. That's where it was introduced. The good news is, though, that if you don't want to spend any money on licensing, it works on all editions of SQL Server, so even Express edition, you can run it in. And if you're really clever as well, you could actually create a Docker container with Dev Edition and run delayed durability in there if you really want to, but I'm not sure why you'd want to do that other than to play around with it. Microsoft are actually trying to drive towards a synergy between the SQL Server on Windows and SQL Server on Linux, but there are certain areas that do not currently work on Linux or not yet implemented that work on Windows. The good news for delayed durability is it works on both, so this is really, really great. And one big surprise to me is that delayed durability works in any logging model that you have. So even in simple logging model, it will work. I did actually have a question from a friend a while ago thinking that if he was running simple recovery mode, it wouldn't work. And yeah, it's totally fine because you'll see later, what we're actually doing is we're just making the mechanism more efficient for our log writes. This will all become obvious later on. So, starting a recap. What are the ACID properties? So the ACID properties are things that a database has to adhere to for transactions, and there are certain levels of compliance. The A stands for atomicity, which means that if we have a transaction, everything within the transaction has to either successfully complete or if there's a failure, we want the whole thing to roll back. So if you owe me some money and I owe you some money, but I don't pay you, so there's a bit of a failure there, I still get your money. That would be great for me, but it wouldn't be great in a banking scenario. So we want, if we have a failure of payment there, we want that whole transaction to roll back. So that's atomicity. I'm going to demonstrate why that's broken in SQL at the moment. C for consistency. There's a few different explanations on consistency if you look at some of the research material. It's really a bit of a mixture. So consistency is that we want consistent results. If we do an operation, we expect that operation to be done the same way every single time. But there's another explanation on consistency which basically states that the database has to be left in a consistent state at all times. So what that really means is that you don't have some form of corruption being introduced to the database by that operation. But it's a bit of a mixture of that. You basically just want consistent data. The I for isolation, so SQL Server introduces the ANSI isolation levels, and the isolation levels really govern what transactions do. I'm sure all of you are pretty familiar with that. By default, we run read committed in SQL Server, which is a pessimistic isolation level, and this is an on-disk model, which means we get lots of locking and blocking. And then, obviously, we have the optimistic isolation levels that came in SQL Server 2005, read committed snapshot and snapshot isolation, and they're optimistic, and what that means is that we have slightly better concurrency because readers don't block writers and writers don't block readers. This is all achieved via the version store, which is stored in tempdb. And then we had the optimistic isolation levels implemented within in-memory OLTP. So it's the same thing, snapshot and read-committed snapshot isolation. They work ever so slightly differently and give ever such slightly different behaviors in certain scenarios. However, you can just think of them as the same thing, but with an in-memory model. And they're obviously very, very efficient. And then, of course, we move on to the thing that this session is about today, the D for durability. So if we commit a transaction, that transaction is committed. We expect that transaction data to be there. So if we have a system failure, it still has to be there. So you as a DBA, for instance, if you have a transaction that's committed, you have a failure, so you've not had a checkpoint operation, it will basically mean you as a DBA will have to take a log backup in order to get the tail end of that log, and then you'll implement your recovery pattern to get to that point. But basically, that data that's committed has to be physically there in the transaction log. So is there any questions on that? That's fairly rudimentary, I'd say. Good. Again, this is old news, so let's try and draw on this slide. I don't normally do this, so bear with me. Talking about transactions, we can define them in different ways. That didn't draw, did it? So let's try again. So explicit transactions, we're explicitly defining the begin tran, and then we have all our operations within, and then we're explicitly defining the commit tran. Now this is a time where if we have any failure within there, we expect the whole thing to roll back to provide atomicity. We have the other default scenario whereby you have auto-commit transactions. So if you don't define a begin tran by default, then each operation is transactional in itself. So if you're doing a very large update and there's a failure, then obviously we want everything to be rolled back within that update process, which is good. How many people here have heard of implicit transactions? I might ask you to explain it then. How many now? Very confident man there. Yeah, so those people that know about this, I hope you'd agree with me in saying that they are evil. It was really a scenario that was introduced for Oracle developers to come over to our platform. I think it was, forget now, but I think it was SQL 6.5 it was introduced. And basically what this is, if you set implicit transactions on, when you start an operation, that will open up a transaction. It will create a transaction count of 1, which means you have to explicitly commit that. Now, the problem with that in SQL Server is it gives very confusing scenarios whereby you can't really figure out how many commits you need in some situations. So I'll give you a great example here. If I set implicit transactions on and do a begin tran, I would still expect, really, that I should only have to commit once because we've just got the one transaction there. But we've explicitly defined a transaction and we've implicitly turned implicit transactions on. Therefore, there are a transaction count of 2. So you have to have 2 commits, which is a bit crazy, I think. In Oracle, it works great. In SQL Server, it doesn't because we're all used to doing it how we normally do it. So just completely avoid it if you can. I think I'm right in saying here that implicit transactions aren't supported with delayed durability. I'll need to just double check that one. So that's a really good thing. And we also have distributed transactions. It's not too relevant to this topic. I think at the end, I basically just go on to say that again, they're not, distributed transactions aren't supported with delayed durability. So it's just ignored, essentially, delayed durability. But distributed transactions, for those that don't know, is essentially you've got 2 different servers and your transaction coordinator is making sure that the change across a remote server is committed or fully rolled back. We can get some interesting scenarios there as well. Right, so let's delve into this transaction definition here. So at the top, we've got our outer transaction, our begin tran. Now, I'm going to prove to you that there are no such thing as inner or nested transactions. It doesn't actually exist, and I will prove it to you. Because when we create a transaction, the transaction counter goes to 1. If we then do another begin tran, can anyone tell me what the counter then goes to? 2, perfect. So you'd think nested transactions do exist. Well, I will hopefully prove to you that's not the case. But for every begin tran, we do need a commit. And another thing to say about nested transactions is that we think of them, or if you haven't really looked at this, you might think of them as being atomic units, or again, they're not. We have this concept in SQL Server where we can define a save point. So in this specific situation, what I've got happening here is I've got some error handling here, and I'm catching any errors that happen, and this is where we run our other nested transaction. If we get a failure in this bit here, then we'll catch that error and we will then, I've drawn on this too much, but we will then do a rollback to that save point. So that kind of gives us that behavior we were seeking with atomic transactions, atomic nested transactions, kind of, but they're not the same thing, or atomic blocks, should I say. Is there any questions on that bit? No? Don't be shy. Right, so let's go straight to a demo. So all my code is on GitHub. I'll give you the link later. I probably need to, it's not really changed much within the last month or two, so it's probably good to go now. My slides have changed ever so slightly, so you might want to wait for a few days for me to upload the slides. But basically, when you download my demo code from GitHub, there's a setup file here. Just load up into your instance and run it. I'm fairly sure, I mean, I think there's one or two explicit paths that you may or may not need to change for your environment, but I'm pretty sure that everything else is pretty good and there's no explicit references like that. So just run setup and you're ready to go with this. And I did this earlier before the session started. Oops. Oh. Right. So the first thing I'm going to do here is I want to prove to you that nested transactions are a myth. And I'm just going to clear down the transaction log buffers here, or at least from our query results. First thing I'm going to do is I'm going to open a transaction, and we will check for a begin exact log record. So for every operation in SQL Server, we have a log record. How many people think there is going to be a log record here? Done a begin tran. I would. Is anyone else? Are you all sleeping after lunch? So you're all correct, of course, because I wouldn't ask the question otherwise. And the reason that's the case is it's a deferred operation. Why do we need to have a begin tran log record there at the moment? Because we haven't changed anything. It's just an efficiency that's been built into the product. So if I do an insert, what will I now see in the transaction log? I need someone to answer this question. So anyone? Going to do a query from the transaction log? Will someone want to shout out? 2. 2's correct. Let's take a look. And that is, of course, the begin record, which is there, and the insert operation. Right, so I'm going to create our first nested transaction. So we've got our first begin, our insert log record, and then we're doing a begin. So now what am I going to see? 2 still? 3? 3? There's some 2, some 3s, so we'll do this, and it's still 2. So we could say, well, perhaps that's been deferred. So I'm just going to do another insert of a record, and then we'll query the log records, and you'll see that we've got our 2 inserts and our 1 begin, but not the other begin. So if we do our first commit, so we've now only got the transaction count of 1 open transaction there. Check the log records again. Nothing appeared. And then let's finally commit and see what we then have. So we've done our commit, we've got no open transactions, and you'll notice that there is simply just 1 begin, 1 commit. That proves to you that nested transactions don't exist. They are just a programming construct for us, or a logical construct. Right, this next demo, we're going to talk about the atomicity and how that's broken by default if you're not a great programmer. So we're going to create a Borg table, and you might notice that I'm sticking a primary key on the ID. Now I'm going to run this transaction below, so who wants to tell me what's going to happen? Perfect. So what are we going to see when we check the table? Nothing? Okay, yeah, so you say it rolls back then. Okay, that's exactly what I would think as well. And we get a primary key violation, but I'm a bit troubled. I've just run this script, so I'm a bit troubled because I'm seeing this one row affected, but we've had our violation. So there's something weird going on here. So I'm going to investigate this a little bit. Let's just make sure that we don't have, if I can learn how to select code, we don't have an open transaction, so we either committed or roll back. And if we query that weapons table, what we see is this. The first 4 records committed, we had a violation, and the 6th record also inserted, and that whole thing committed. So we didn't get a rollback. The key takeaway here is there are certain conditions in SQL Server that do not cause a rollback. They're considered not necessary for atomicity. In this specific scenario, the explanation I always give, or I've been told, is that this was implemented a long time ago in SQL Server for the scenario where you might be loading lots and lots of data and you get that one violation, you don't want the whole thing to roll back. I don't like that at all, and I personally think that it should. Now, there are lots of ways around this. I think I give one in this script, so let's just move down a bit further. Oh, no, I don't, strangely. One scenario is we can set exact abort on, which will basically give us the behavior we expected. If we have any strange error, it will make and force that transaction to roll back. But the problem with that is that will also introduce a scenario where, I think it's called uncommitted transaction. I forget the exact error you get, but basically if you turn that on, and let's just say you've got some error handling as well. So let's say you get an error and the rollback starts happening, you've got your catch block, and maybe you want to do a bit of logging into another table. Problem is that transaction has to fully roll back, and that extra data you're trying to create in another table is extra logging and part of that transaction, so it has to roll back. So that will cause another error or a different error. But basically, the takeaway here is, as developers, you need to be aware and you try and use exactly the same patterns. And the other, and probably the best way to get around this problem is to use the try-catch error handling, and in your catch block to do an explicit rollback. So you definitely, yes. Yeah, so the question basically was, if you set exact abort on, will it roll back everything? Yes. If you look at, this was going back to when I didn't have any facial hair and had only just started using SQL Server, and I thought SQL Server was purely atomic, and I saw this command and thought, what is this? And I started to look at the description, and it basically told me what I thought SQL Server was already doing basically doing a rollback on an error. So, yeah, I advise you to basically read the MSDN blurb on that, and that's exactly what it does. There are no conditions in SQL Server that will not roll back on any errors. Moving on, so that's atomicity. So we'll move into isolation here. This scenario is a real scenario that I've run into in a fashion industry, and basically what was happening, somebody came to me and said, this is really weird, we're losing loads of stock in our warehouse, tens of thousands of pounds, but then some weeks we're actually getting a bit of extra stock. We don't really know what's going on. So me thinking the worst of everyone, I thought, oh, it's the warehouse staff stealing stuff, and then they're putting stuff back in case they, get caught, they've taken too much, I'll put a bit back. So I always think the worst of people. And anyway, I thought, okay, leave it with me. I'll look at the code and see what I can find. And I started to profile the load, and you could use extended events if you want to, if you're advanced. And I basically found the piece of code that was doing this behavior, and you'll see in a second what was happening. So what we're going to do here, I know it's not very good, the text there, so we'll just flip back into this code. Very simple code, got declaring a transaction, we're assigning the current quantity value to a variable and decrementing one off that because we're selling an item of clothing. And then we're updating that value back to a table and committing. Cool. And I'm going to run it at the moment. In fact, I don't even need to do it in SQL Query Stress right now because we're just, oh yes I do, 1,000 iterations under one thread. So this is a serial load here. It's just one person basically buying all this stock and paying 1,000 times, essentially. And just double check, did I ensure? Just double check that. Just double check the weapons table does have 1,000 at the moment. So, for all those of you that are good at maths, you would expect if somebody buys an item of clothing, or in this case a weapon, 1,000 times, you would expect the amount in that table or stock level to be 0. And hopefully I'm correct in saying that. So great. I'm a junior dev, I've released this code, and the business is booming now. We don't have a lot of traffic, but people are starting to buy stuff, so I'm close to a promotion. Unfortunately, when we get a bit more busier, there are issues happening, and my promotion is now in the balance. So this time, we're going to have 100 people, 100 iterations and 10 people purchasing this weapon. Just double check it before. So I thought I did reset it. So we've now got 1,000 items back again. And if I run it, hopefully we won't get any errors. So we've had 1,000 iterations again, but this time with 10 people doing it at the same time. Can anyone tell me what we're going to see? Are we going to see 0 stock items? More than 0. How many more? Behavior of the threads. Yeah, pretty much. Anyway, you're not allowed to answer questions because you're a bit of an expert. I'll tell you what, you can answer questions if no one else is answering them. Does everyone agree with this guy? I've kind of given away he's telling the truth here, haven't I? So let's have a look. 808. So that means we've had 808 lost updates. This is what was happening in this fashion company scenario. The funny thing was, though, when I fixed this code, the warehouse burnt down about a week later. They had a fire in a warehouse, and they lost all the stock. And it made national news at the time. And that made me think, was there something else going on that I didn't know about? I don't know. So maybe there was somebody stealing things and a dodgy bit of code. Don't know. We'll reset the table again. And there are quite a lot of fixes to this, but the one I just did so in this scenario, it might be worth me explaining what is wrong with this code, in fact. So what we're doing here, we're running read committed isolation, and what we're doing here is we're assigning a value to the select. Now, if we've got lots of threads doing the same thing, they might assign the same value. So they're basing their decrement on the wrong value, or what will possibly be the wrong value if this one commits. And if you've got lots of them doing it at the same time, this is where we had 808 lost updates. So what you really want to think about is having these delays between your code. You can't afford these delays in your code with the locking model. Because unless we're running serializable, which would fix this, but would get lots of deadlocks happening, which means that you'd have to keep replaying the transaction. Okay? Is that clear? Cool. So my fix was fairly simple. I just tried to remove the decrement in the select and assignment. It was in C# code, to the assignment of the variable in C#, and actually just tried to put it in the update statement itself. And I can find where that code is. There. Not there. So conceptually, exactly the same thing. 110 threads. You see that's pretty darn quick as well, which you'd also expect, because we're doing less operations. And that works. There is actually there's quite a lot of fixes to this. There's one that I haven't really seen anyone discuss, but I did come across this in an Oracle book fairly recently as well, whereby, so this may be a valid fix. What you could do is when you're actually writing to the quantity, you could stick in your where predicate where quantity equals what value you think it was. And what that would mean is that you'd obviously have to have extra error handling there, because what if it isn't? But what that would mean is that even if, let's say we had 3 threads running, one decremented, but one returned stock back to that table, we've still got the value that the third one thinks was there. So it would actually be a valid decrement, even though the data has theoretically changed. So I don't know, it's something you might want to think about. So anyway, we've shown lots of strange behaviors now with the acidic properties. So let's just flick back into the slides. Was there a question somewhere? No? Right, first thing, we're going to talk about the log file. And, well, most of you will probably, if you don't, well, you are German, so you're highly efficient and highly knowledgeable. But if you're an audience full of British people, you would think that the log file, or the log itself, was just a log file. That's not very efficient, because when SQL Server has to commit data, having to write straight to a file is going to put lots and lots of contention and overhead there. So the architecture is this. We've got these in-memory constructs called log buffers, and when we make changes are made in memory to these log buffers as log buffer records. These were the things we were querying earlier. And then, so when we get a commit, that will cause the log writer to flush that log buffer to the transaction log. And there is another scenario where you might get log flushes. So it's physically persisted at that stage in the transaction log, those changes, which is exactly what you want when you commit, because we're basically saying we want a guaranteed ability to be able to get back that data. So the other scenario is if the log buffer's full, why do we keep it around? We might as well just flush that down. There's a slight inefficiency there, because we'll have records which might need to be undoed if a transaction doesn't actually commit. So this is why you have undo records in your when you're doing recovery on a database. There's also a really, really ambiguous behavior why you might get flushes, and this happens on checkpoint. You'll have to do a lot of digging around to find this in documentation, or at least you did when I looked. And it's very hard to explain, because if I don't look at this slide for a long time, I forget, and I'll forget how to explain it. But essentially, so those of you that have really knowledgeable or semi-knowledgeable will know that when you do a checkpoint in SQL Server, that basically pushes all your changed data pages or flushes your data pages to the data file. So it hardens them to the data file. Some of those may be part of committed transactions. Some of them may be part of uncommitted transactions. Okay? Now, it may be that, so on a checkpoint, it could be that some of those data pages are related to early LSNs, logical sequence number, so log records with a logical sequence number which was earlier than your records there in another buffer. So that means that that buffer will then also have to be pushed down because you can't have out-of-order log records in the transaction log. So that's a bit of an ambiguous scenario. However, there are different reasons why a log buffer will flush by default. What we're doing in delayed durability is we've got the same situation here, but the problem is if you think about it, every time you do a commit and a log buffer has to flush to disk, that's a physical IOP. That may be really inefficient because let's say we've just done one insert of one record, and that's it, commit, flush. That's an awful lot of flushes we're going to get, and I think they're 60K in size, these log buffers, so that's an awful lot of inefficiency there. So delayed durability basically says, when you commit, don't flush. But obviously, that leaves us open to data loss. Because commit is supposed to be a guaranteed durability, guaranteed that the transaction is there and persisted in the log. With delayed durability, we can also flush a few other ways. Again, when the buffer is full, it will flush. We can also run per databases SP flush log stored proc. And there is also another scenario, which I found interesting when I heard about this, is that if you have a durable transaction that's run within that database, that will also cause a flush. So you might think if we implement delayed durability, and this I initially did, we're going to get really far behind, and if we have a system crash, we're going to lose so much data. In reality, it's really not like that. You'll lose a little bit of data. So you need to think about systems that you're implementing this on. And also, another thing, I say this later, another thing to also bear in mind is SQL Server may or may not use delayed durability if you set it. There's no guarantees that it will use it. So how do we actually set it up? It's really, really easy. We can basically force a database so that all transactions in that database are delayed durable. I advise doing that if you're about to leave a company and they've not given you very many pay rises and you're leaving on bad terms, just flick that option to forced and then leave. Don't tell them about it because they'll potentially lose data at some stage. Another option that you can set is disabled if you want to stop anybody using it. So even if I specified to use it in my code, it would stop that being used, or at least it would stop that delayed durable happening. And the one that we probably want to do is the allowed. And then if we do that, we can basically turn on delayed durability on, per transaction for on-disk or in-memory tables. Or we can set it to on for atomic blocks. You'll see this shortly. This is quite a quick demo, and given the time, because we've got roughly about 20 minutes, I'd rather show you all the demo before we complete the slides. So, okay, so this is on disk, delayed durability for on disk. We're not using any in memory here. First thing I'm going to do is just make sure delayed durability is disabled. And grab this piece of code here, and I think we run it 3,000 times under 10 threads, which is 30,000 transactions. And next thing to tell you about is I've set up perfmon, and we're monitoring transactions per second and log flushes per second. So the log flushes are the log buffers being persisted to the log file. So we can get a general idea of throughput, and we'll also look at the elapsed time as well. So hopefully we won't get any errors here. Now, if we go back to perfmon, you can see that the transactions per sec is ticking along nicely. They're under the same scale as well. And log flushes per sec obviously has overhead here. So we are getting a fair few log flushes happening. Flip back here. Somebody remember for me 19.4 seconds, because I will forget. Now I'm going to force delay durability, so we don't need to change our code here. Exactly the same piece of code. Again, doing 30,000 inserts. Well, 30,000 times 4. But 30,000 transactions. Flip back here. And I don't know if you agree with me, but I think we're getting an ever such a slightly higher transactions per second and getting very, very little log flushes. And hopefully the duration of that was less. 16. Wow. Made 3 seconds. Yeah, everybody wants to hire me now, don't they? So that's on disk. I'll tell you what I'll do, because it's probably better I go back to the slides to explain InMemory. How many people here are using InMemory? Hardly anyone. Okay? I'll try not to spend too long on this. Again, technology came in, SQL Server 2014, and basically we've got a bit of a problem in our old pessimistic model or old optimistic on-disk model in SQL Server. There's quite a lot of bottlenecks. As you've seen, there's quite a lot of inefficiencies with the way the transaction log works. We've got lots of locking, lots of latching going on. So Microsoft basically put a lot of research into InMemory, and what they did is they came up with a completely brand new model in which all the data rows and all the index rows are basically in memory. Now, one of the things that they still need to do, though, is they still need to persist the data on disk, because if you have a system failure, you still need to read back your data into memory. But there's a slight difference the way they do that, because this operation to populate our checkpoint file pairs, where the data ultimately goes, is asynchronous. Because the mechanism for the transaction log works identically pretty much within memory as it does for on disk. So all the changes that are made are in a transaction log. Now, one of the key things here is or to bear in mind, is if you're making changes to a row in memory, that row is not touched. A brand new row is fired up, and that old row, once we get a commit, is then just marked for removal. So because of that, if you get rollbacks, then there's nothing to undo at all. So we don't actually need to push any changes that haven't committed down into the transaction log. All those changes are deferred, essentially. There's two types of in-memory. You can have schema-only in-memory tables, which is massively efficient. We pretty much get 0 transaction log overhead from those, because there is no data to come back. You lose everything in the table. That's brilliant for staging tables. Or you can have, I think it's schema underscore data, so schema and data tables, which are exactly what I just described earlier. And there's this thing called log block compression. So the scenario I showed you where you have one log record per operation, that goes now within memory. I've got a demo which I will try and squeeze into this presentation, which shows you how InMemory compacts these log records before persisting it in a transaction log. There's basically lots and lots of log improvements. So if you've got a massive overhead or bottleneck in your log file, then InMemory, in the right scenario, is something you should seriously look at. I think that in-memory for BI processes is an absolute must, especially for stuff like staging tables. Also, good point here in the bottom is all index operations are not logged either. So if you're doing an index rebuild, the overhead to you, from a resource perspective, is memory, because it will basically do a copy of that data in memory, and it doesn't need to log anything in the transaction log, because all that's recorded is the definition for that index. So if you have a system failure, all the data is loaded back into memory, and then that index definition is fired against your table, and an index is built in memory. So some fantastic things there, but obviously there's a bit of a downside in startup time, or potential startup time. Right, so now we can go back to the demo on the in-memory delayed durability. So what we need to do is we need to create a special in-memory OLTP file group here. You'll see contains memory optimized data. And we will create what's known as a container in-memory speak. You can think of it as almost like a database file. I have to warn you though, if you do this in production, you cannot get rid of the in-memory file group once you've created it. So make sure you want it. So we've done that now. We're ready for in-memory. I'm going to create our in-memory table. And the thing that probably might be worth me talking about is this bucket count. What is the bucket count? Bucket count refers to a hash index. So if we've got values like my name, Mark Broadbent, so first name, surname, if we create an index on those two things, a hash index, then we create a hash value. Now, how selective that hash value is, or how unique that hash value is, will depend on how big our bucket count is, because a bucket is a memory location. So if we define a very small bucket count, then we will get what's known as hash collisions if me and you have completely different names, which I'm sure we do, but our hash, because we've defined a small bucket count, might collide. Was there a question somebody shouted out? No? So the advice is you basically need one bucket per unique index value, but then you may have growth as well. So there's quite a lot of information out there describing how to size your bucket count. Is that a question, is it? No? Just stretching your arm. Anyhow. Bear in mind here, this durability, schema and data is nothing to do with delayed durability. This is the basic saying we want in-memory tables that are durable. So we've now got everything. We're ready to go. We've got our in-memory table. Let's just disable durability on the database. And same code, but to our in-memory table. If we flip back 16 seconds, I think it was, wasn't it? So again, we're getting our log flushes, which we would expect, because I said to you the log mechanism works pretty much identically for in-memory tables. I'm hoping this is slightly quicker than, well, it was quicker than the on-disk. So interestingly, the delayed durability on-disk beat the in-memory table. Certain scenarios in memory is great, others it's not as good. But now, what I'm going to do is force delayed durability, so we're using in-memory and delayed durability. And that's the same code again. Again, our log flushes are pretty much down at 1-ish. And you can see the transactions per second definitely looks a little bit higher. And thankfully, it's 14 seconds now. So that's not a bad improvement. I've shaved off 4 seconds. So you can see we are getting tangible performance benefits with delayed durability, but they are a compromise, and is it worth the compromise yet? Not sure. So what I'm going to do here is create something that is called a natively compiled stored procedure. It's basically an in-memory stored procedure. There's a couple of downsides to using those because you cannot query on-disk tables. That's what we're doing earlier, or that's what we could have done earlier with the way we were touching our in-memory table. We could have done a select and a join across from our in-memory table to an on-disk table, and that's called using the interop. But here, we're basically using an in-memory stored procedure, and we have to query in-memory table. So pretty much the same code again, but as a natively compiled stored procedure. Behind the scene, what did that fail? Invalid object name. Ah. There we go. Thank you very much. So behind the scenes, this is compiled into a DLL. The DLL is linked in process to the SQL Server process, and that code is then called via SQL Server when you run your code. So now our code is essentially this exec statement. Right, I've not been very impressive so far, so I want people to shout out what the time's going to be, because I'm not really sure myself. So I've taken about 6 seconds, is it 5 seconds? 5-6 seconds off the processing time. Who thinks we're going to get down to 10 seconds? And I really don't know right this moment. Yeah, you do? Anyone else? Anyone lower? A couple people lower. I'm not too sure. I hope we will, so let's try it. There's something interesting going on here as well. Yay, 8.7 seconds. That's a pretty good improvement. So we're running delayed durability and natively compiled. But something really weird is going on here, and it's basically, you'll notice there's no transactions per second happening. And I won't bother showing you it because it is documented in my code here. Microsoft, in their infinite wisdom, created a brand new counter for XTP transactions when it's natively compiled. So you've got to go to a completely different counter set and then pull that out. And the downside to that as well is it's not per database, it's for the entire instance. So if you're trying to do metrics on how much I improve things, if you've got a lot of in-memory activity going on, you won't be able to know what it relates to. So not a big fan of that at all. Okay. I'm going to show you the bonus demo as well before we flip back to slides. We have got 7 minutes. Similar sort of thing where we're looking at log records. And let's clear this down. So you've seen this before, and we expect to see, well, I'd expect to see approximately 6 values, the begin, the commit, and then the 4 inserts. Which we do. With in-memory logging, you remember I was saying that there is this thing that I call log compression. Pretty sure I wrote a blog post about this about 4 weeks ago. Because the way that SQL Server for in-memory defers the commit log records to disk, it's able to, because if you think about the in-memory constructs and it's making changes, now saying to you there is no undo going down at all, it's only when that commit happens that then we do have to push something down, and because that operation is deferred, it can do something with those log records. So we're going to clear those log records out and do an operation on our in-memory table. Now we may see and in here, it might be worth me explaining this code to you. What we're doing in the first bit of code is we're looking for what's known as a LOP HK or logical operation hecton record. So this will be one record. And then in the next piece of code, we're kind of taking that record and running another function over it and cracking it open and seeing what's inside. So I'll run the whole thing. So this is actually what is in the transaction log itself. You'll see our begin transaction record, our commit, and we've got one single log record for about 4 inserts, whereas before we had 4. Now imagine if you've got massive transactions, you've got a lot of inserts going on, and then multiply that by how many people are doing stuff. You can see there's a substantial amount of log saving to be made. Less log writes means better log throughput. So we've cracked this open, and then down below, you can actually see there are the inserts inside that. I believe that this update record is related to the index that I've got on this in-memory table, because on this one I didn't have any index on it at all. In-memory tables, you have to have an index. Okay, so I think that update's related to that. Yeah, so some great efficiencies to be made within memory, especially if you're having log issues. Right, so, sorry. How do you monitor this stuff? How do you know if you really need this stuff? Well, I would actually argue if in certain scenarios, I wouldn't even need to know that our system's having problems to implement certain things. I would know, for instance, that if I'm creating a table that is just a staging table and going to be thrown away, then, and that's a repeatable process, then why not do it as a delayed durable thing? Why not? You're getting benefits from it, and all these little benefits you're going to get by doing that is going to add up to a healthy system at the end of the day. There are some things to look out for, though. Write log weights you might see in systems where your log file is definitely having performance problems. So it could be that your underlying disk is just not keeping up with the amount of log changes that are happening. The top one, log buffer, I'd need to look that one up, but I think that, obviously it's a problem, but I think that would also indicate you might have memory pressure on your server, but I'd need to look up that weight type. And the third system view, the third line down the system view there, I find this an incredible way to look at your database file health and the throughput. The scenario is I had a SAN engineer basically saying, oh, the SAN's working fine, there's no problems at all. And I queried from that, and that basically tells you all the I/O that's happening, all the latency, pretty much everything you need to know. And this is accurate stats. This is how long that it takes to push that stuff out to your physical disk. So you can query that and go back to your SAN engineer and say, there you go, and leave it to them and send them a link to the explanation of that. And the guy in question that I did that to basically came back and said, yeah, there is a SAN problem. And then finally, the other counters you might want to use is what we've already used to look at your transaction throughput. It's probably worth knowing how many transactions per day your system goes through. And as I say, you can do this per database normally, but if you're using natively compiled, that kind of skews your stats a little bit. Got 1 minute to go, so very, very quickly, there are certain conditions where delayed durability is ignored, such as if you're using CDC, those records have to be in the transaction log for CDC to pull the things off. And I've put this big red block here because I've found, I'm a bit of an HA person, and I've found if you're running HA in companies, your operations guys get very, very clumsy with your SQL Server. It's like, yeah, we can fail it over and do some patching, so we'll just fail it over. Thing is, if you're using delayed durability, you might not want them to fail it over at that stage because you're doing some kind of operation that you really don't want to have that switching and forcing you to lose data. But it was your stupidity as well to put that scenario there in the first place, I guess. So be careful if you're using HA. So, should we use delayed durability or not? I would basically say, in the right scenario, yes. I probably wouldn't bother using delayed durability, apart from just best practice for those tables where I don't want to use in-memory and I don't want to use natively compiled, but I just want to have ever such a slight optimization on my staging tables. But if I had the full reign of my server, for those scenarios, I would look to going to natively compiled stored procedures and delayed durability, because that's the thing that you get the most benefit from. Final point, though, is you've got to use it in the right scenarios. You can't take any risk with this. If you turn it on and even lose one transaction, I would personally say you as a DBA or developer or even a BI guy have failed. BI guys generally can reload stuff, but the rest of us generally can't. So be very careful, but give it a whirl. And finally, you can get my GitHub stuff here. I'll try and give the SQL Conference guys the slides as well. I'm sure they're going to be publishing them. And please rate the session and be very, very kind. Thank you very much, guys.